tired. Stay awake. We are dealing with 8.2 and their properties of acids and bases. We're going to focus on the acids because most of the bases stuff falls into the acids, or at least the reactions that we need to know. So if we think back a couple of units to precipitation reactions, we were required during that time to look at what reactants I had and predict what products I would get. That's the same sort of thing that we're going to see here, where we're given some reactants and we have to identify what type of reaction is going to happen and therefore what products we're going to get. And there's 3 basic types, so if you know the 3 basic rules and you remember stuff from first semester, you're going to be able to do all of these problems with ease. We're not talking about putting an acid or a base into water and seeing what happens anymore. We're not trying to do Bronsted-Lowry, we're not trying to do Lewis, we're not trying to do Arrhenius. It's none of that stuff anymore. Now we're talking about actual reactions, like what we saw in the lab on Friday and today. That's actually going to be the first type that we look at. So we're looking at how acids react with different types of things. So let's start out looking at your standards. So you have your standards packet out. We're in topic 8.2. It's the second page. Please take a moment to read through understanding and understanding 1 and 2 so you know where we're going with this. Read understanding 1 and understanding 2. Okay, so our first reaction is what we did in the lab. We had copper and we had zinc. One of those two had a reaction. Which one was it? The zinc was, because that's the one that should have anyways disappeared. And you should have been left with your copper, and that's because copper is very unreactive. But again, like I said earlier, reacted with nitric acid. So it's still going to have this sort of reaction depending on what the acid is. So an acid, each of these are with acids, acid plus a metal. That's what we're dealing with in the first one, acid plus a metal. And we know metals are almost the majority of the periodic table. So an acid with any of those metals, assuming the reactivity is good enough, should form 2 things, salt and hydrogen gas. Did we observe hydrogen gas formation on Friday?
Yes.
Yeah, how did we observe it? The bubbles. We saw bubbles, and you might see a problem like this on a test, and they might ask you what gases formed. So they'd say you took, I'll just go with zinc because that's what we just did. You took zinc and hydrochloric acid and you get a gas. What gas is it? That could be a question on an IB exam. They like taking real life examples now. They're trying to weave more lab stuff into their problems. So start anticipating, like, okay, what we're doing in lab actually does matter because they're going to put it in terms of this. We'd be able to figure it out, though, because we know that an acid and a metal forms salt and hydrogen gas. Now, it's just a metal not bonded to anything else. So we're thinking metallic bonds. We're not reacting it with an ionic substance or anything at this point. It's just with a straight-up metal. Any of the metals from the periodic table with any of the acids that we have. And they form salt and hydrogen gas. So salt is an ionic substance, and I want you to write that down. So we use salt as this general term. It's an ionic substance that's formed from a reaction with an acid. A salt is just an ionic substance. Salt is just an ionic substance. So written on the board, on the far side of the board, I have the reaction that we did in the lab. I had zinc plus HCl, forming ZnCl2 plus H2. I want you to think back to first semester, and I want you to show me with your hands what Roman numeral is the zinc. What charge does the zinc have? What Roman numeral would it be looking at ZnCl2? I am seeing a bunch of 2s. Why are you saying 2s? Can somebody raise their hand and tell me why? Go ahead, Chloe.
Because the charge of the zinc would go to the charge of the chlorine.
Yeah, exactly. The chlorine was a 1 negative, And the zinc must have been a 2 positive, so when we crisscross them, that 2 came from the zinc. The one that's behind the zinc came from the chlorine. Beautiful. What questions do you have before we move on? I have a question for you then. Why H2? Diatomic. Yeah, it's diatomic. And that leads to another good question. So is this reaction balanced? It is the way we have it right there because I have a coefficient of 2 in front of the HCl. So that's the balanced reaction of what you completed in the lab just last Friday and through today. Same sort of thing in this example. So I have hydrochloric acid and lithium this time. Looking at the periodic table, find lithium. We are going to do some good reviewing. So think about, don't shout anything out yet, think about what group lithium is in. What's the name of the group? Okay, if you know it, go ahead and shout it out. Nice, alkali metal. It's in the first column, so it's an alkali metal. See, we're already getting ready for finals. Woohoo. Why is it just LiCl and not like Li2Cl? Something like that. Go ahead.
Because lithium has a 1
Mm-hmm.
negative charge, 1 positive charge,
Mm-hmm.
and chlorine has a 1 negative
Mm-hmm.
charge, so they
Cancel out.
out.
Perfect. So we've got lithium with a 1 plus, Cl with a 1 negative. When they crisscross them, they cancel out. It's neutral overall. Good. Good, good, good. And that one's balanced the way that it's written there. Second reaction is one that we have done many a time before, or at least earlier on in this year. When we react an acid with a base. Acid with a base. Again, remember all of these bullet points that we're doing are acid with this thing. So this one's acid with a base. And the base can either be a metal oxide, so any of the metals with oxygen, or a metal hydroxide, so metal with an OH1 negative. Again, we'd crisscross them because it'd be an ionic substance. They're going to also form salt and water. So not hydrogen gas for this one, but water. And we don't just write the salt with an AQ. It's not going to balance correctly, so we actually write whatever my salt is plus H2O. This salt, we'd have the AQ for aqueous behind it, but we have to write out plus H2O. What state would the water be? Liquid, yeah. Sorry. Exothermic. Exothermic. The beaker would feel what to my hands? Hot. Yep, or warmer than it was before. It's releasing energy. Very good. Okay, I said we did this one before. We did this one back when we had a burette, which was that really skinny, graduated, bless you, instrument that we used with an Erlenmeyer flask below it. And we had base in the burette, and in the little Erlenmeyer flask below, we had hydrochloric acid. We also had an indicator. Does anybody remember what indicator we used? Okay. Abe. No. Phenolphthalein. Yes, phenolphthalein was what we used in that. What color did it turn when I had just an excess of base? Just barely an excess. Pink. It turned pink with just an excess of base. If you were able to get that one where it was one drop one way, one drop the other way, where it was going back and forth between clear or colorless and clear and pink, going back and forth that way, that's a point where technically I could have drunk it because it was salt, as in table salt, because the leftover was NaCl. My water comes from the OH and the H. NaCl was left over. So I had table salt in water. Technically, I could have drunk it if I was sure that I was doing a good procedure. And this is the scary part, phenolphthalein is really toxic, so I wouldn't have wanted to drink it with the phenolphthalein in it. But theoretically, if we took sodium hydroxide and hydrochloric acid and got them exactly even, I'd have salt water. Not that you'd want to drink salt water. But still, I'd have table salt and water. Is this one balanced?
Yeah.
It is, yeah. Some people forget that I have hydrogens in 2 different places. That add up to that 2 that I have there. But it is balanced if you saw both of those hydrogens. So that's my second reaction. Again, my base can either be a metal oxide or a metal hydroxide. Some people forget the metal oxide part of that. Don't forget the metal oxide part. And then I have, finally, one that you've probably been doing since you were a teeny tiny tot. An acid with either a metal hydrogen carbonate, a metal carbonate, or a hydrogen carbonate. And an example of this would be vinegar and baking soda. Been doing it since you were a teeny tiny tot. So what gas were you forming when you took baking soda and vinegar and it started bubbling? CO2, absolutely. Formed a pretty heavy gas, so we would have been able to see the rate of the reaction by the gas leaving the beaker.
Why was it like
Scale.
bubbly? What was the liquid? Was that just excess?
So the liquid that's left over could be some of the excess vinegar, but mostly it's salt dissolved in water. Yep. So this example, rather than with baking soda and vinegar, is with hydrochloric acid, zinc carbonate, zinc 2 carbonate, because it's a transition metal. I want to know the Roman numeral for it. Zinc 2 carbonate, forming zinc chloride, that's my salt, water, and CO2. I want to go back to baking soda and vinegar, though, and I want you to look through your notes if you don't remember it off your top of your head. What was the most common term, or the best IUPAC term for vinegar, or the chemical that's in vinegar? I want to give everybody a chance to look for it. Give me a thumbs up when you find it. And I'm not looking for acetic acid. I'll tell you that much. I'm not looking for acetic acid. I'm looking for the other name. When you have it, give me a thumbs up. That's okay. And we've got almost everybody with it. What I would like you to do is, as a class choir, please tell me, what is the name for the main component of vinegar? Yay! You guys got it together, too. Very nice. Ethanoic acid. Beautiful. Yay. It is not. No, that's a good point. Let's do fingers. Show me with your fingers what I'm going to put in front of the HCl to get this one balanced. I'm seeing a bunch of 2s. Very nice. So I'd put a 2 in front of that. I'd have 2 hydrogens. And on this side, I have the 2 hydrogens from the water. I'd also have 2 chlorines from the 2 chlorines that I have there. 1 zinc, 1 carbon, 3 oxygens, and 1 + 2, 3 oxygens. Questions before we move on? Okay, we're going to look at our standards again. Your standard this time is 8.2 guidance 2. I'll have you look at that before I flip the slide. 8.2 guidance 2. If you don't have those standards, they're in the back. 8.2 guidance 2. So we are dealing with indicators. I'll give you a few more seconds to read through it. What?
I don't like that Ivy spells color with the U.
Oh, I know.
Everywhere else except for
I know. That is funny.
Program.
Yeah,
Oh, yeah.
and me programmer. Okay, indicators are things that change in predictable ways to show whether an aqueous solution is acidic or basic. So that's what an indicator is. They change in predictable ways to show whether an aqueous solution is acidic or basic. And we're going to talk through some of the common indicators here. And if you can leave at least a little bit of room on the bottom of the page, we'll have one more slide after this. So don't write what I put up next too large. I'm going to post these all. I'll let you write them, then I'll talk through them. Okay. As the name suggests, blue litmus paper is blue in color. And when you put blue litmus paper in anything that's acidic, it's going to turn red or pink. If you take that blue litmus paper and put it in anything else, so either neutral or basic, it's going to stay blue. Just going to stay blue, either if it's basic or neutral. So it will give us a clear indication if there's an acid, but it's not giving us a clear indication if it's neutral or basic. So then we get to the red litmus paper, which is starting out as kind of a pinkish color. When I put that in bases, it turns blue. But just like the blue litmus paper, if I put it either in an acid or in a neutral solution, it stays the color that it was before. So it's a good indication for if I have a base, but I can't tell the difference between neutral and acidic. So that's why quite often if you're doing a blue litmus test, you're also going to do a red litmus test. Because if it turns both of them, or if neither of them turn, so the blue litmus paper stays blue and the red litmus paper stays red, then you know it's neutral. If one of them changes, then you know whether it's an acid or a base. If neither of them change, you know it's neutral. But we kind of have to do those two tests together to be able to identify what it is. Phenolphthalein, we've used this one before. In bases, it turns pink, otherwise it's colorless. Notice I'm using the word colorless and not clear. Clear means transparent, you can see through it. Colorless means it has a lack of color. Methyl orange, in acids it's going to turn red. In bases it will be yellow. Kind of an orange to start with in neutral. And then this is one you can do at home, red cabbage juice. You can make some cabbage juice by taking red cabbage, chopping it up, putting it into boiling water, leaving it for a while, then straining it out, and the liquid that's left over, if you put it in either acids or bases, will change color. Red for acids, blue for bases. We can also use what you did in the Le Chatelier lab with tea. You took black tea and we changed the hydrogen ion concentration. You just didn't think about yet what that was doing, and we saw a change because it was an indicator. Now, since Mr. Alm didn't talk about what you were doing with that one, I added points to everybody's Le Chatelier lab, just so you know. So that's what was really going on there. So T is another indicator. Universal indicator is one of the ones that IB really wants us to know, and this is why I said leave some space at the bottom of your page. Don't flip the page because that's not the notes that we're doing yet. We're staying at the bottom of the page that we're on right now. And you don't have to draw all of this out. The main things is this is the pH scale. I want to make a note that this is pH scale, which we'll learn more about tomorrow, or no, 2 days from now. Tomorrow, who knows what we're doing tomorrow? Lab. We're doing a lab tomorrow. Neutral is going to be a green color. Neutral is at 7. It's going to be green. Again, you don't have to write this all out, so if you're frantically writing out and not listening to me, you're going to be writing way more than you need to. Right now, all that we've written down is neutral is at 7 and it's green. You can do an arrow to the right. You can write a 14 at the very end of that. And you can either write alkali or you can write a base. Base is the word that we tend to use. Alkali means the same thing. So you can write either of those. I'm getting more basic as I go from 7 to 14. And just write down that the shades are turning to a dark, dark purple as we go to the right. So it goes green to blue to dark purple.
Would 14 be considered black?
Potentially. It's really a dark, dark violet is what it should be. It looks black up there, but it's more of a violet. And then as we go from neutral to 0, we've got acids. We're getting more acidic on our pH scale. We go from green to yellow to orange to red. Green to orange to yellow to red. And that's all that you need to write down.